In this video, we're going to be looking at the logarithmic function. So in the previous video, we took a look at a new function called the exponential function. The logarithmic function is the inverse of that function. So just like multiplication and division are inverses, addition and subtraction are inverses, and they undo each other. They do opposites to a number. The logarithmic function and the exponential function are inverses. So here we have the definition of a logarithmic function. Well, first of all, here is how we write the logarithmic function. This is read log base a of x. So you have this number here, which is a base. Just like when we have a function b to the x, b is called the base. Okay, the actual definition of the logarithmic function is here. So y, a number, equals log base a of x if and only if this is true. So basically what you have to learn from this definition is that whatever answer you have for your logarithm is the exponent in the exponential function. The base a of the logarithm is the base a of the exponential, and whatever you're taking the logarithm of here becomes the answer here. So basically your x and your y kind of change places. So let's just use this definition to evaluate f of x equals log base 2 of x if x is 32. So to simplify this or evaluate it, we're going to replace f of x with y, and we're going to replace x with 32. Then we're going to use this given definition to rewrite this equation. So x is what you're taking the log of, so our 32 is the answer. The base a is the base here, right? That's 2, and then it's raised to the y power, right? So basically what I'm trying to do is figure out which exponent that I put on 2 would give me 32. And that answer is 2 to the 5th, right? You could just start multiplying 2 until you get to 32. So that means that y, right here, would equal that 5. Okay, so that's how you simplify a logarithmic function. We'll try one more. So we want to evaluate log base 10 of x when x equals 1 over 100. So again, we replace f of x with y, so we have an equation that we can rewrite. We have log base 10, and our x is 1 over 100. So that means, if we go back to our definition here, that 1 over 100 equals the base is 10 to the y. Okay, so just like with our exponentials, we have to remember some of our exponent rules. So first of all, I have a base 10, so I want to change this to a base 10. So I'm going to rewrite that as 10 squared equals 10 to the y. And now to move this to the top, I can make the exponent negative. So this becomes 10 to the negative 2 equals 10 to the y. So y has to equal negative 2. So that means that this log, right, log base 10 of x is equal to negative 2. Okay, so now I want to introduce or show you some properties of logarithms. Clean off my board. So there are some things that are always true when we're working with logarithms, just like there are with exponentials. And if we know what those properties are, it will make simplifying and solving equations simpler. So we know that log base a of 1 is always 0. So the log of 1, no matter what base you're using, is always 0. And that is true because anything to the 0 power is 1. So these logarithm properties follow straight from what we know about exponentials. The log base a of a is always 1. So when you have the same number here and here, you're always going to get 1 because a to the 1 is always a. Log base a of a to the x is just x, because here you have the logarithmic function and you have the exponential function. They are inverses. They cancel everything out, so you're just left with 1. So that is because also a to the log base a of x is x, right? They're opposites. So when you apply both of them, this is actually called the inverse property. And then lastly, if the log base a of x equals log base a of y, then as you might expect, x equals y. And this is just, we had one of these with the exponentials. It's called the one-to-one property. And so it's true for logarithms as well. So let's use these properties to simplify some expressions. So we want to simplify log base 4 of 1. Well, we have a 1, and this property here tells us that it doesn't really matter what your base is, you're always going to get 0. So when you have a 1 here, your answer is always 0. Now let's look at the log base square root of 7 of square root of 7. So at first you look at that and think that looks pretty complicated, but if we go back to this property here, right, that shows us that if these two numbers are the same, no matter what they are, our answer is always 1. Let's look at 6 raised to the log base 6 of 20. So this is our inverse property, right? You could look here or here. When the base here and here are the same, they just cancel each other out. So this 6 raised to the log 6 really goes away, and you're just left with the 20. Okay? Now let's look at some equations that we could use these properties for. If we have log base 3 of x equals log base 3 of 12, well, this one's pretty simple with our one-to-one property, right? If the log and the base are the same, then we can just drop them and we have x equal 12. Similarly, if we had, say, log of 2 to the x plus 1 equals log of 3x. Now here we don't have a base written, but it's assumed to be 10. Log base 10 is the most is one of the most common bases, and so when it is base 10, it's just not written. So when it's omitted here, right, that means this is base 10. So they're the same bases, so now we can just set the two other parts equal, and we get 2x plus 1 equals 3x. So now we have a simple equation that we can solve. We can subtract 2x from both sides, and we'll get 1 equal x. Okay? So the last thing that I need to show you with logarithmic functions is called the, is a special logarithmic function. So just like with exponentials, we had the e to the x, which is the natural exponential function. We have a natural logarithm that is the opposite of that. And so it is when you have log base e, this is called the natural logarithmic function, and it's usually abbreviated LNX. So natural log instead of that looks like an exponent, so let me rewrite it. Okay, so when you're dealing with base e, that's natural log x. It comes up in a lot of applications, so it has its own abbreviation, LNX. So the properties are exactly the same as the properties with regular logarithms. The natural log of 1 is 0. The natural log of e is 1 because that is the base that we're using, right? The natural log of e is 1. So all of these properties are written in your textbook. You can look them up. They're in a little box definition, but they're no different from the ones that we look at for any logarithm. So we can use those same rules to simplify something like the natural log of 1 over e. If you remember our Okay. So if you remember our logarithm properties that say when we divide, we actually subtract, this can be rewritten as the natural log of 1 minus the natural log of e. Well, the natural log of the logarithm of any 1 is always 0. And logarithm of e, because this is the base that it's defined as, is 1. So this simplifies to negative 1. We could also do something like e to the natural log of 5, right? Well, these simplify here. They are the same, right? The natural log of e and e cancel, and you're left with just 5. So you should be able to use those properties in the same way to simplify these.